screen visible?
Yes, sir.
Okay. So here we are now starting fiber optic communication lab. How many of you have joined? Okay, 43. Okay, so uh, so you see these are the course outcome objectives and outcomes. So what is the objectives? That demonstrate fiber optic analog link and digital link. Then to know attenuation, losses, numerical aperture measurement, then modulation, some coding, coding technique and some modulation techniques. Then optical amplifier, uh, then WDM and DWDM system. Then what is the outcome is that what technical abilities you will have, technical qualities you will have. So you can design fiber, single mode and multi-mode fiber. Okay. Then you can choose modulation techniques for certain communications like short distance or long distance. That means short haul or long haul communication. Then optical amplifier and then interferometers. So these are the experiments. Uh, you see that first experiment is related to design of fiber optic analog link and fiber optic digital link. Second experiment is based on fiber attenuation measurement and numerical aperture measurements. So there are two aims. One is measurement of fiber attenuation, another is measurement of numerical aperture. Then third experiment is PWM and PPM techniques. Okay. Understanding or realizing PWM and PPM techniques in fiber optic link. Next experiment is analog time division multiplexing. That is time to see how the time division multiplexing takes place through optical fiber. Then we'll see fifth experiment, that is digital time division multiplexing, then how digital time division multiplexing takes place. Sixth experiment is Manchester coding and decoding in optical fiber link. We'll see how Manchester coding is performed, like what is the circuit, what is the transmitter and receiver circuit, how coding is implemented. Then seventh experiment is related to measurement of bit error rate and study of I pattern in fiber optic link. Eighth experiment is WDM and DWDM system. WDM systems. Ninth experiment is related to modes. Okay. Visualizing the modes and characterizing the fiber based on modes, LP01, LP11, etc. Then 10th experiment is based on Mach-Zehnder electro-optic modulator. That is how very high frequency signal, that is in the range of gigahertz, is converted into light signal. That is done by Mach-Zehnder modulator, or that can be used for some sensing applications. So then next experiment is Manchester coding and decoding using software. And last experiment is regarding the amplifier, fiber amplifier. So there are total 12 experiments, out of which 8 experiments is based on hardware kits, and last 4 experiments are based on software. These software are only available in lab only. We use 2 softwares. One is beam propagation software, beam prop. Another software is OptiSystem, OptiWave. So OptiSystem software is actually for simulation of whole optical communication system. Okay. So we know that it is very difficult to perform laboratory experiments sitting in online mode. It is also nowadays has become difficult for engineers to do practical experiments in online mode. But what we can do from our side, that we'll demonstrate the experiment, okay, in front of you. We can see it online, and you have to take the readings and you have to draw the graphs. That thing can be done, and each time I'll do the experiments along with the lab technician. Okay, so through mobile I will show the lab experiments and all the kits which are available, and then demonstrate. And for software also we will do the same, but one software, that OptiSystem, you can download it, okay, OptiSystem, but that remains valid for 1 month. That is uh, for evaluation purpose only. So they give time for 1 month, I think. So you can use that, you can do that experiment on yourself, and that one is the same thing is done in lab also. Okay, so let us start. Let us introduce. Let us give some basics related to optical fiber communication. Okay. You know that this course information sheet I will upload in the team and the team file. You can see the list of experiments. Now I will explain some of the experiments now. Okay. So first experiment is fiber optic analog link and fiber optic digital link. So basically, what do you mean by fiber optic link? Is that there will be some source. Okay. This is source. Then transmitter circuit. Okay. Then optical fiber. Then receiver circuit. Then it is destination. So this is called fiber optic link. Okay. So here this is the light signal, electrical signal, and here you see optical signal, and here also you will see electrical signal. Do you see the screen?
Yes, sir.
Okay. So now this, any fiber optic link, first thing is needed, that is transmitter. Transmitter is composed of light source and another is circuit, electronic circuit. Light source generally of two types. One is LED light source, another is laser source. Okay. So the purpose of light source is to convert the electrical signal to optical signal. So if your electrical signal is sinusoidally varying, the optical signal should also sinusoidally vary. Now, this actually, the frequency, it is different thing. This frequency is the frequency of electrical signal, but this frequency is actually a modulated signal. Okay. It is the envelope of the very high frequency signal. Okay. The intensity is actually intensity of the light is varying according to the message signal. But this frequency is what? Can you tell? This frequency is what? Can you guess what is this frequency?
Sir, frequency of the electrical signal, message
No.
signal.
This message signal frequency is this one, that is the envelope. Okay.
Yes, sir.
I am talking about the inner signal, inner waveform. What is the frequency of this?
Sir, frequency of optical wave.
Yes, frequency of light. Okay. That is the optical frequency. This falls in terahertz range. That is 193 terahertz. If it is wavelength is 1550 nanometer. Okay. If it is 1550 nanometer, then you will get 193 terahertz signal, okay, light frequency. And this frequency is kilohertz or megahertz, whatever it is, message signal. So you are superimposing the electrical signal onto a carrier signal. Carrier is the light signal. Okay. Now, the laser, the LED and laser. Okay. Two types of light sources are used. What are the characteristics? LED is broadband, broadband light source. Okay. And its spectrum is broad, that is lambda versus intensity. and this is generally 50 to 100 nanometers. And laser, whereas it is monochromatic. What is that frequency? That is very narrow beam. 1 to 2 nanometers. Whatever the wavelength may be what? Wavelength may be 800 to 1500 nanometers for any source. These are the available 1550s, let us say. These are this wavelength range are used for optical systems. Earlier 800 nanometer was used. Nowadays 1550 nanometer is used. But if we use 800 nanometer laser, okay, 800 nanometer laser, then that means here we get 800 nanometer wavelength, and here plus 50 minus 50, let us say it is 750, and at this point it is 850 if you consider this span. Whereas if you use this is 850, so it is plus minus 1, minus 1 plus 1. So within this range laser operates. Now what is the difference? What is the difference between the operation of laser and LED? LED is used for short distance communication because of as it emits many wavelengths, which creates dispersion. So for short distance communication, if dispersion is negotiable, then we can use. But whereas laser, it is used for long distance communication because it emits very few wavelengths that allows less dispersion. Now in earlier, the LED were used, that is gallium arsenide. Okay, LED or laser, whatever it is. The material was based on gallium arsenide, and it allows the wavelength of 800 nanometers, 600 to 800, 600 to 800 nanometers. But when the ternary alloy or this thing, indium, gallium arsenide, phosphide, quaternary. So this allowed to operate the fiber at 1550 nanometer long wavelength, no long wavelength, okay, long wavelength region, that is quaternary, and this is homo junction, and this is heterojunction. Okay, do you know difference between homojunction and heterojunction? West PN device.
Yes, sir.
What is it?
Sir, if we take a PN junction, PN device, sir, so if homo means the level would be same, and if
Hmm.
it is a hetero means there would be in the middle, there would be a material where the height is less.
Height means what height?
I mean, the the width of the region.
No, actually not width. It is band gap. Okay. So
Yes, sir, band.
suppose this is your P and this is your N. Okay. PN. If the band gap EG1 and the material of band gap of N, EG1 is equal to EG2, then it is homo. And EG1 not is equal to EG2, it is hetero. So like quantum well structure, this is actually here one PN junction, PNN, NPP, PNN, this is N, this is P, this is P. So all these band gap energy are different. These two, there is a junction, it is different. So it allows better carrier confinement, okay, and wave guiding capability. So you will study all when you will study theory. So why we talk about this? Because of the property of optical fiber. If you see the characteristics graph, that is fiber attenuation. Fiber attenuation, that is alpha versus lambda. It is dB per kilometer. So it is seen that this kind of graphs are there. Here also some peaks are there. This is a loss graph. This is a loss curve. Okay. So for different wavelength, there is different loss. So there are generally three window. One is near about 1550. One is 1300. Another is 800. So nanometers. Okay. So earlier this window was used for operation, later on this window, and lastly nowadays this window is used. This was used, and but this is the universal graph of silica fiber. Okay, silica fiber. So earlier this is the first window. This is second and this is third. So earlier this was used because light sources, earlier light source and detector were available. Nowadays the light source are available, light source or detector available at this wavelength. Now what is the meaning of it is that if you choose this wavelength 800 nanometer, here loss is comparatively high. But here at this wavelength, loss is least and also dispersion is minimum. Understand?
Yes, sir.
So that's why the wavelength that is chosen 1550 nanometer for nowadays optical communication, this 1550 nanometer is used because of the technology or material available, that is light source material available at this wavelength. Okay, that is this one, indium gallium arsenide phosphide quaternary alloy, four element semiconductor. Many advanced light sources, laser diodes are there depending on the applications. Okay, these are used now. So these are all about the light sources. Now, uh, what is the principle of light emission? Light emission, what is the principle? That is a forward biased PN junction. Okay, forward biased PN junction. So that means, say, let me draw the band diagram, that is P and N. Okay. So if you apply forward bias, then electron will jump to this higher energy level, to this one. They will cross the barrier and go to P region. And here holes are available or you are supplying. Okay. So this is electron. This is electron. These are holes. Now electron does not want to stay at higher energy level. It will try to come down to lower energy level and recombine. By this way, it emits one photon. photon is emitted. Similarly, these holes also, there are other holes which will go towards this side. So this way, the electron and hole continues to flow in the p-n junction, and we get emitted light or emitted photon h nu. This h nu is nothing but hc by lambda, and this lambda is actually the wavelength of light emitted. So in this case, we have to use direct band gap semiconductor. Can you give example of direct band gap semiconductor? Anybody please respond.
Sir, normal PN junction diode.
Normal p-n junction diode. This is direct band gap semiconductor. You tell about the material. Okay, material. There are many semiconductor materials like silicon, germanium. Okay, so are these direct band gap?
No, sir.
You have to know that what is direct band gap semiconductor and what is indirect band gap semiconductor. Can anybody of you among this class can tell who have taken VLSI specialization? Who has taken? Harshvardhan, you have
Yes, sir.
taken?
Yes, sir.
You should have told, no? You should tell.
Yes, sir. I got confused in that. Mostly direct gap band materials. It is combination of two materials, sir, like
Hmm.
aluminum and gallium, like that. Materials we take
Hmm.
and combine.
Like gallium arsenide. Okay, gallium arsenide, aluminium gallium arsenide. Okay. These are all direct bandgap semiconductors, and they are only capable of emitting photon, and other semiconductors emit the heat energy. Okay, they can be forward biased, but they cannot emit photon, indirect bandgap semiconductors. So we cannot use silicon, or germanium because they are all indirect material. Due to the recombination, they emit heat energy or phonon. Sometimes it is called vibrational energy, called phonon, not photon, phonon. So we cannot use indirect band gap semiconductor for LED or laser or for light emission purpose. we have to use direct bandgap semiconductor. Now, what is the meaning of direct and indirect bandgap semiconductor? That I am not, that I am leaving up to you. You see what is the definition of direct bandgap? Okay, because generally the momentum of electron and hole should match. Then only the energy level. If you see the energy diagram, okay, the momentum should match. EK diagram. Okay, that should match. Then only it can radiatively recombine. Radiative recombination and non-radiative recombination. Okay. Then next, then I will discuss about light detection detectors. So for light detection, PN junction should be what kind of bias, reversed or forward? For light detection, PN junction should be reverse biased or forward biased.
Sir, reverse bias.
Who told reverse bias?
Sir, Harshvardhan Agrawal.
Okay. Yes, reverse biased. PN junction should be reverse biased. All other people are listening or not? Please raise your hand. Other people? Yes. Yes. Okay, but you should respond at least. After a long time we are meeting. I think you have forgotten me. Have you forgot me?
No, sir.
Okay. Okay. So light detectors, PN junction should be reverse biased. Why it is reverse biased? Again I am drawing the energy band. Now it is more down inside. Okay. Now here the basic thing is that in the depletion region, we focus on the carriers of depletion region. The electron should stay in the valence band. Okay. So now if some light detection means if light falls on it, then this electron will gain energy and will go to the conduction band. So we'll get electron hole pair. Okay. So electron is staying in its valence band. If you reverse bias it, then that means ensures that electron stays in valence band. Then electron hole pairs are generated. These are called photocarriers. That is carriers that are generated due to photons, photocarriers. Now, these holes will be attracted towards negative supply, and these electrons will be attracted towards positive supply. So current flows. So current flows, that is called photocurrent. Photocurrent flows due to flow of electrons and holes. Okay. Now this current, that means one photon will generate one electron hole pair. Okay. One photon will generate one electron hole pair. That is the principle of light. But here in this case, simple silicon or germanium can be used as material. Now there are two types of photodetectors. Types of photodetectors. One is avalanche, another is pin photodiode. Okay, I am not discussing the structure of this, but I am just telling the names. So this is called APD, avalanche photodetector. This has gain high. But requires large voltage. So it has gain low, low voltage. Now photocurrent is in the range of microamperes. Okay. That is very, very small. So we need to use always photodetector followed by amplifier. Okay, because output is contains noise. Photodetector is low voltage plus noise. So you have to use some amplifier. Okay. So this is called receiver. This is called whole the optical receiver circuit. Understood?
Yes, sir.
Okay. Now we discuss about optical transmitter. What are the things should be there in optical transmitter? Can you tell? ऑप्टिकल ट्रांसमीटर में क्या क्या होना चाहिए?
Sir, there should be a drive circuit and a light source.
Yes, it is light source LS and driver circuit. Okay. Generally, this is actually written before this one. The driver circuit, then light source. Light source is basically a diode. Okay, this is a simple diode, and you can use BJT based circuit, driver circuit. What will be the circuit? Simple circuit is, let us say, one transistor we use. Here one VCC, simple resistance, then diode. In place of resistance, so here the photon will be emitted, and this is your message signal. It may be sine wave, square wave, etc. So at the output of the LED, intensity will vary according to message signal. Light intensity. Light intensity will vary according to message signal. Okay, so that means if this signal, input signal, is applied at the base, so the base current will vary, so the collector current will vary accordingly. Collector current vary means it is flowing through the light source, that is PN junction device, diode. If diode current vary sinusoidally, then also intensity will vary sinusoidally, because the relation between the light intensity versus current, okay, that is called PI characteristics. It is linear. Okay. If it is varying sinusoidally, this will also vary sinusoidally. If it is square wave, then also it will vary square wave. On off blinking, square wave means it will blink. The LED will blink. Okay. Now, this is all related to light source and detector. Anything you want to know about this light source and detector?
Sir, there may be a time delay in between, no?
Time delay, yes, obviously. Time delay means what? It is actually response time. Okay. So immediately when once the input signal is applied, immediately the light is not emitted. And depending on that, the frequency of the signal or bandwidth of the system is dependent. That is called rise time. Okay. Rise time or response time for both light source and response times for detectors. Generally, if you use a BJT transistor, so there is, we talk about that if you take the signals from collector end, the collector terminal, then it is 180 degree out of phase. Okay. Phase difference between input and output is 180 degree. But if you take from the emitter terminal, it is in the same phase. Okay. So there is no such problem in response time. Okay. Response time of LED, although there are certain matters like modulation bandwidth. Okay. When we will modulate the light emitting diode, okay, generally carriers are there, charge carriers, electrons. Okay, so though they have those kind of characteristics like carrier lifetime, okay, recombination lifetime, effective carrier effective lifetime, tau effective. Okay. So this carrier lifetime actually determines the bandwidth of the bandwidth of the modulation or message signal. So you cannot you cannot give very high frequency signal to a simple transistor because there is limitation or carrier lifetime of the device. So there is some term related to for light source that is called modulation bandwidth. Okay. So you will probably you will study, and also you can find in the book when you will study the LED topic, modulation bandwidth, that is related to 1 by tau effective carrier lifetime. At the same time, photodetector also has the parameter of response time, responsivity. Okay. So and also RC time constant. RC time constant is there in photodetector. So it is when you will square wave input, immediately signal does not change from 0 to 1. Rather, it takes some time. That is called rise time. Okay. So rise time is dependent on the capacitance of PN junction. Okay. Capacitance plays a big role in bandwidth. Okay. Because it determines the time constant RC. Okay, so if capacitance is less, C is less, then time constant is less, then switching from 0 to 1 or 1 to 0 will be faster. Okay. So to increase the capacity, to reduce the capacitance, generally some intrinsic layer is provided in PN photodiode. Okay, PN photodiode, PN junction is sufficient, but this intrinsic layer is intentionally has the advantage that it reduces the capacitance by widening the depletion region. If you use intrinsic layer, then depletion layer will increase. Any device, any PN junction device. So if you use wide depletion layer, one advantage is that the capacitance gets reduced. That means time constant gets reduced and it will be fast. Bandwidth will be more. But at the same time, it has to travel, the carrier has to travel larger distance, longer distance. That is slightly a problem because transit time will take place. Transit time problem will be there. So you cannot keep very high, long depletion region. Okay. So there are many issues because this subject is actually combination of electronics and physics, okay, optics. So that's why people have developed many techniques for converting the lights, electric signal to light by means of optical techniques. Okay, it is all optical techniques. No electronics will be involved. No transistor. No no other with low frequency kind of devices. All devices with high frequency. That's why some modulator, Mach Zehnder modulator, okay, and high frequency photodetectors are generally used. Okay, so that are beyond our scope of discussion now. So now coming back to optical fiber. Okay, now we'll discuss about optical fiber. So optical fiber can be classified in many ways based on material, based on mode, based on index profile. Okay. So Western material, it is glass or plastic. Western mode is it is single mode and multi-mode. Based on index, it is step index and graded index or any other classification. Western material, mode, index profile or any other classification. Material, mode, index profile. Okay. And also nowadays microstructured fiber, microstructure, PCF, photonic crystal fiber, dispersion based. Okay, whatever it is, others, let's say others. Okay. So now, what do you mean by glass fiber and plastic fiber? Glass is made from silica, SiO2. Plastic is made from polymer. Glass fiber has low loss and polymer fiber is lossy, but some advantage is there. And last, it is used for long distance because loss is less, and it is used for short distance. Single mode and multi-mode. Actually, single mode is for long distance, as loss and dispersion are both minimum. In multi-mode, short distance, okay, but dispersion is high. Now, what do you mean by single mode and multi-mode? Single mode means electric and magnetic field orientation is of one pattern or single pattern, whereas multi-mode is many pattern. Light propagation can be explained in two ways. One is through rays, another is through wave. If you use ray optics, single mode fiber light goes straight, but in multi-mode fiber many light propagates with different angles with the fiber axis. This is single mode fiber and this is multi-mode fiber. In terms of rays, but in terms of modes or waves, you have to analyze the electromagnetic field pattern. You have to know the electromagnetic field pattern. Let us draw one such electromagnetic field pattern, like say HE11 mode. That is hybrid mode. Both magnetic and electric field are present. And this is called LP01 mode. Linearly polarized mode. If you see the electric field distribution of this LP01, it is actually this kind of electric field distribution, or you say at the center it is dark. Okay. At the center it is dark. A single plot, a single spot would be there. That is LP mode means what? It is a it is means degenerate mode. It is generated from He11 mode only. Okay. So uh, and other modes are there, LP11 mode, let us say. It has this kind of polarization. Or that means two spots will be there, and at the center it is dark. Okay. LP02, two rings will be there. One this ring, another ring. So these are EM waves. So when light propagation is explained through EM waves, then it is called modes. Okay. When light propagation is explained or analyzed by means of electromagnetic waves, then we talk about modes. It is actually certain electromagnetic field pattern. Okay. So these are this is single mode fiber. This propagates only in single mode fiber. And condition, now we'll discuss what is the condition of propagation of single mode fiber. Condition of light propagation of single mode fiber. That is V number. That is important term. That is fiber parameter that is given as K K0 ANA, where K0 is 2 pi by lambda free space propagation constant. A is the radius and Na is the numerical aperture. N1 square minus N2 square. What is numerical aperture? Numerical aperture is, it defines what is the maximum, what is the maximum acceptance angle. So this is your, what is the fiber structure? Let us discuss. What is the fiber structure? Fiber structure is made from core and cladding. This is refractive index N1, this is N2. Refractive index. What is refractive index? That is C by V. That is velocity of light in free space by velocity of light in medium. So this is N2 and N1. That is core, and it is surrounded by cladding. Refractive index is N2. Now numerical aperture is defined as n0 sine theta 0 max. Okay, n0 is what? The refractive index of the medium from where light is appearing, and this is coming to be root over n1 square minus n2 square. So this, to know the light propagation, you have to know the V number. So for single mode fiber, V number is less than equal to 2.405. This is the condition for single mode fiber. Light propagation in single mode fiber. Only LP01 mode propagates. Okay. For V number greater than 2.405, V number less than 3.8, it propagates LP01 plus LP11. For V number greater than 3.8, LP01 plus LP11 plus LP02. I think there is some upper limit, 6 or 7, I think, that I have to think of. Okay. So there are certain criteria. So that plot is actually, it is called BV plot or beta, that is coming from this. Beta, that is propagation. So some certain condition is there. Okay. So these are all about light propagation for single mode fiber. So when we design the fiber, you have to choose the parameters lambda, radius, n1 and n2. But apart from this, some other criteria are there. So now uh, what we are discussing regarding fiber. Okay. So we have discussed material, mode, then index. Okay. Index is step index or graded index. Step index means throughout the core region, the refractive index is constant. This is N1, this is N2. This is core and this is clad. And graded index, it is something like profile or and it is clapped. This is N2 and this is N1 R. Okay, radial according to radius, refractive index changes. So, do you have any discussion? Do you want to ask anything?
No, sir.
Anybody else? So in the next day, I will continue this discussion. I will not start the lab now. Okay, then now I stop here. If you want to discuss anything on any matter, then you can ask me. Or you may leave.
Thank you, sir.